Welcome to the channel where we bridge the gap between classic geological principles and the cutting-edge technology defining the future of Earth science. Today we are diving into the indispensable concept of integrated geosciences, exploring how the deep synergy between geology and geophysics is solving some of the subsurface's trickiest puzzles. This is not just about using two datasets side by side, it's about marrying them through advanced computational techniques like joint inversion and artificial intelligence to create models that are dramatically more reliable. Historically, geologists and geophysicists have approached the Earth from two distinct yet equally important vantage points. A geologist is often described as the historian and material scientist, focusing on direct observation and material composition. They look at physical samples, outcrops, and high-resolution well logs to determine rock type, age, and depositional environment. This is hard data. It is definitive about composition at specific points, but inherently sparse and expensive to obtain. On the other side, the geophysicist is the remote imager, applying the rigorous principles of physics and math to sense the Earth's physical properties. They collect vast amounts of data, seismic records, gravity, magnetics, and electromagnetic surveys, which provide spatially continuous coverage of the subsurface. This is often called soft data. It is everywhere, but it is mathematically ambiguous because many different subsurface structures can produce the exact same geophysical measurement. Some jokes suggest geophysicists are just geologists who happen to know math, but in reality both disciplines are foundational and must cooperate. Both disciplines share the fundamental goal of building an accurate predictive model of the Earth and its history. This complementary relationship is key. Geologists define the rock properties and structure at discrete points, providing crucial boundary conditions and context for the geophysicists' models. Geophysicists then bridge the vast gaps between those sparse data points, providing continuous imaging of structures, geometry, and fluid conduits, essential for understanding the 3D subsurface. The problem of ambiguity: why standalone methods fail? Why can't we just run a geophysical survey and call it a day? The biggest challenge in geophysics, especially with potential field methods like gravity and magnetics, is the problem of non-uniqueness. Essentially, there are infinite possible models of the subsurface that could generate the observed gravity or magnetic data at the surface. This inherent ambiguity means standalone inversion models are often poorly constrained and unreliable. For complex geological interpretation, imagine trying to guess the shape and material of a hidden object just by measuring its gravitational pull. A small, dense sphere could produce the same reading as a large, less dense cube. You need additional information. What rock types are present, what densities are plausible, and where are the known boundaries? Geological data is the essential prior knowledge used to reduce this search space, transforming uncertain possibilities into physically plausible realities. In exploration, this non-uniqueness translates directly into risk. The risk of drilling an expensive well based on a model that looks good mathematically but makes no geological sense. The only way to systematically mitigate this risk is through quantitative data fusion. The solution: advanced joint inversion, the marriage of data. Joint inversion represents the high-tech marriage of multiple geophysical datasets, sometimes including geological constraints directly in the mathematical process. The idea is to combine mutually complementary data where the ambiguity of one dataset is compensated by the sensitivity of another. For example, seismic data might map structure well but struggle with fluid contacts, while electromagnetic data might map conductivity, fluids well but lack fine structural resolution. Combining them yields a superior result. For years, joint inversion relied on knowing the empirical relationships between different physical properties, such as a simple linear correlation between seismic velocity and density. However, in complex geology, this relationship can change wildly from one rock unit to the next, limiting the method's effectiveness. This challenge led to the development of novel joint inversion methods, often called multiphysics data fusion, that do not require a priori knowledge of these specific statistical relationships. These new approaches focus instead on enforcing structural similarity between the models derived from different geophysical measurements. One powerful family of these approaches uses Gramian constraints. The Gramian, a mathematical operator, essentially measures the correlation between different model parameters such as conductivity and magnetic susceptibility or their transforms. By minimizing the Gramian term in the inversion process, the system is forced to produce models where the boundaries and gradients of the physical properties align. This ensures that the final 3D models share the same subsurface geometry, even if the absolute values of the properties are independent. It's like ensuring that while a dense layer and a conductive layer might have different measured values, their physical boundaries perfectly match, corresponding to a single geological interface. Another technique involves joint focusing constraints or minimum support stabilizers. These methods force anomalies of different physical properties to either spatially overlap or undergo rapid changes at the same location. This is highly effective in locating discrete mineralized bodies, forcing the highly magnetic and highly conductive zones associated with massive sulfide deposits to occupy the exact same volume of rock. We have seen this put to the test in mineral exploration sites, such as the Reid-Mahaffy test site. When airborne electromagnetic AEM and total magnetic intensity TMI data were jointly inverted using Gramian-based structural constraints, the resulting model showed a high degree of structural correlation between conductivity and magnetic susceptibility. This dramatically enhanced the subsurface image of the target mineralization compared to the murky, indistinct patterns derived from standalone inversions. By fusing these complementary datasets, geoscientists gained a level of confidence in the 3D geometry of the target that was simply unattainable before. The accelerator, AI and the hybrid revolution. As powerful as joint inversion is, the arrival of artificial intelligence, AI, and machine learning (ML) is transforming the entire geoscience toolkit. AI is accelerating seismic interpretation, integrating diverse data types, and expanding analytical capabilities at an unprecedented speed. It's important to clarify. AI supports and enhances the geoscientist's judgment. It does not replace the human expert. AI is making its impact felt in 4 key areas that directly enhance integration. 1. Generative AI models. These emerging tools, such as diffusion models, can create synthetic subsurface data and generate plausible geological scenarios for testing and validating models. This helps fill the pervasive gaps left by sparse drilling data. 2. Agentic AI systems. These sophisticated systems are capable of running end-to-end geoscience workflows, from data ingestion and processing all the way to basic interpretation with minimal human intervention. This frees up expert time for high-level problem framing and critical decision-making. 3. Vision language models, VLMs. By combining seismic imaging with natural language processing, VLMs can analyze vast repositories of geoscience data and unstructured documents in entirely new ways, connecting text descriptions and geological reports directly to patterns seen in subsurface images. 4. Physics-informed AI, PIA, the hybrid model. This is perhaps the most promising direction for integrated geosciences. Traditional AI models driven purely by data often act as black boxes whose outputs are difficult to physically interpret and whose reliability wanes when presented with data outside their training set. The hybrid model solves this by weaving domain knowledge, the physical laws and fundamental geological principles we know to be true, directly into the AI framework. For example, the mathematical expressions governing wave propagation or fluid dynamics can be used to constrain the training of the neural network. This integration of physics-based approaches with data-driven modeling yields a best of both worlds solution. Models that require significantly less training data than pure AI, and whose results are more accurate, reliable, and interpretable because they adhere to the fundamental laws of nature. The expert geoscientist's role evolves into an orchestrator of these intelligent systems, leveraging AI to manage complexity and volume while ensuring the fidelity and geological soundness of the final models. Applications, the integrated advantage in exploration. The ultimate goal of all this integration is practical success in exploration, where economic risk is high. Whether searching for oil, minerals, or sustainable energy, integrated geosciences are now the imperative. Hydrocarbon and geothermal exploration. In hydrocarbon exploration, the entire process is focused on building a coherent geological model and systematically reducing the uncertainty or de-risking the project through phase investment. Basin modeling is a critical foundational step, integrating geological data like stratigraphy and structure and geochemical information, source rock maturity, with seismic data. This synthesis defines the trapping structures, fluid migration conduits, and the overall architecture of the petroleum system. For example, detailed geological mapping and outcrop studies in the Cook Inlet Basin are integrated with subsurface, seismic, and core data to pinpoint hydrocarbon trapping structures, demonstrating the crucial synergy required for major discoveries. Geothermal exploration demands a similar integrated approach, focusing on identifying high permeability zones deep beneath the surface. A novel protocol for this involves combining surface structural data derived from remote sensing, which maps structural lineaments like faults and fractures, with information from airborne magnetic surveys that image deeper structures. By performing a twofold structural analysis, surface and subsurface, researchers establish the relationship between these lineaments and potential high permeability geothermal fluid pathways, advancing the shift towards sustainable energy resource identification. Mineral exploration. Mineral deposits, often buried deep beneath cover rocks, have characteristic geophysical signatures that require multimodal interpretation. Modern exploration routinely combines techniques like induced polarization, IP, magnetics, and gravity, all cross-referenced meticulously with geological mapping. Geophysical models alone might indicate an anomaly, but it is the geological team who provides the context necessary to differentiate between valuable ore mineralization and surrounding geological noise, such as superficial magnetic minerals. Joint inversion is particularly useful here, as demonstrated by the case studies showing its effectiveness in improving the subsurface images of geological targets. By forcing multiple geophysical parameters like electrical and magnetic properties to share the same structural boundaries, we gain immense confidence in the location and geometry of the concealed ore body. The geoscience future. A hybrid professional. The trajectory of geoscience is clear. It demands a hybrid professional. The next generation of geologists and geophysicists must be deeply versed in both their core domain knowledge and the principles of data science. This fusion of skills is necessary to effectively leverage the complex technologies that are defining our future. Advanced computing resources, including cloud platforms and high-performance computing clusters, are becoming the standard infrastructure needed to run computationally demanding workflows such as full waveform inversion and complex AI simulations. The ability to manage, interpret, and orchestrate these intelligent, complex systems will be the defining trait of the successful geoscientist. We are moving beyond merely interpreting the Earth to actively modeling and predicting its behavior with unprecedented accuracy. The integrated geoscience imperative is truly the key to unlocking the Earth's mysteries, ensuring that our models are not just mathematically elegant, but geologically sound. The traditional division between the rock and the wave is blurring, giving way to a unified, data-driven, and highly productive methodology. If you're interested in these subjects, please subscribe, hit the like button, leave a comment, and share this channel with your friends. Until next time, keep exploring.
Welcome to my channel, where you'll find over 2,000 videos on geology, geochemistry, AI, and many other subjects. If you like what you see, help us grow by subscribing, liking, and sharing this channel.
I think these videos are brilliant, and I'm sure you will like them too. Please like, comment, and subscribe, and don't forget to click the notification bell.